going to finish the semester by talking about improper integrals, which are basically integrals that have infinities or negative infinities in their bounds of integration. And our approach for evaluating improper integrals is going to be writing them as limits. So let's do an example. What I'm going to do is I'm going to find the integral from 0 to some finite number b of 1 over root x plus 4. And then I'm going to take the limit as b goes to infinity. See what happens as that upper bound becomes infinite. So I think over to the side, before I actually do this limit, I'm going to try to find the antiderivative. So I think before I find this limit, I'm going to just try to find the antiderivative of 1 over the square root of x plus 4. I'm going to rewrite this as x plus 4 to the negative 1/2. And then I'm going to use the substitution method. I'm going to let u equal x plus 4. My du would be 1 dx. And then I can rewrite this integral as u to the negative 1/2 du. To integrate, I add 1, so I get u to the 1/2 divided by a half, technically plus c. I won't need it when I evaluate my integral though. And let's see, dividing by a fraction is the same as multiplying by its reciprocal, so this is 2, and u was x plus 4, so 2x plus 4 to the 1/2 plus c, or 2 square roots of x plus 4 plus c. Okay, so that's my antiderivative. So that means when I evaluate this limit, I'm going to be finding the limit as b goes to infinity of this antiderivative evaluated at b, evaluated at 0, and subtracted. So that would be limit as b goes to infinity of 2 square roots of b plus 4 minus 2 square roots of 0 plus 4. So limit as b goes to infinity of 2 square root of b plus 4 minus, that's going to be 2 times 2, or 4. To find this limit, I plug the infinity in for b. So 2 square root of infinity plus 4 minus 4. And infinity plus 4 is infinity. And if you take the square root of infinity, well, you still get infinity. And so what this means is this limit doesn't converge to a number. When we get an answer of infinity, we actually would say that the integral diverges. This means that from 0, x equals 0 to x equal infinity, the area underneath that curve is infinite. Now, sometimes we're actually going to get numbers though, and in those cases, we'll say that our integral converges. So here's example B. We're going to integrate from 3 to infinity, 6 over x plus 5 to the third. Now, technically, we really should be writing this as a limit, but I'm going to show you a little shortcut that I'm okay with in this class. So I want to warn you, the notation I'm using is technically not right, but it always works, always gives you the right answer. And so I think for our purposes in this particular class, we'll stick with my shorthand. So what I'm going to do is, so before I do anything else, I am going to just try to find the antiderivative of 6 times x plus 5 to the negative 3. I'm going to let u equal x plus 5, so then du equals dx. This becomes 6u to the negative 3 du, or 6u to the negative 2 divided by negative 2 plus c, or negative 3u to the negative 2 plus c, or negative 3 over u squared. I guess we should change that back to an x, negative 3 over x plus 5 squared. Okay, so there's my antiderivative. So that means if I want to find this improper integral, the antiderivative is negative 3 over x plus 5 squared. And I'm going to plug in 3 plug in infinity, and subtract them. Again, technically I really should be writing this as a limit, but when we find limits, we end up just plugging numbers in anyways. So I'm going to plug in the infinity, and then I'm going to plug in the 3. If you take a constant like -3 and you divide it by something infinitely large, something that's growing without bound, that is going to go to 0. Anytime you have an infinity on the bottom, it goes to 0. So I'm left with 0 plus 3 over 8 squared. That would be 3 over 64. And so in this particular case, we would say that this integral converges, and it converges to 3 over 64. This is actually telling me that if I were to take the area under this curve from 3 to infinity, I would actually get a finite area. The y values must decrease rapidly enough that even though we're going all the way out to x equal infinity, the area actually converges to a finite number. All right, let's do a few more. Example C. First thing I'm going to do is just try to find the antiderivative. I'm going to use a u sub. I'll let u equal x to the third plus 1. So du is 3x squared dx. That means dx is du divided by 3x squared. So the integral becomes x squared over u times du over 3x squared. The x squareds cancel out, that's a good thing. I can pull the constant of 1/3 out front, and I'm left with a 1 over u du. So that becomes 1/3 natural log of u, or we could write that as 1/3 natural log of x to the third plus 1. Okay, so back to my improper integral. We just figured out what the antiderivative was. And now we are going to have to evaluate this at 0 and evaluate it at -infinity, and then subtract them. So the first term, we end up getting a natural log of 1, which is 0. And then in the second term, natural log of, well, we've got an infinity to the third plus 1, and then we're taking the absolute value of that. That's natural log of infinity, which goes to infinity. Because I don't get a finite number, because I get an infinity, I would say that this integral diverges. Okay, one more example. In this last example, both bounds are infinite, but we can still use the same process. Now, technically, if I wanted to be formal and show my work using a limit, I would actually have to write 2 limits, one for each of those infinite bounds. You can see an example of that in those formulas I kind of listed in the top of the notes. But it turns out if both bounds are infinite, my shortcut works as well. So first thing I'm going to do is integrate. The antiderivative here should be 1 over -5 e to the -5x. And then I have to plug in my bounds of integration and subtract. So -1/5 e to the -5 times infinity minus -1/5 e to the -5 times -infinity. So this is -1/5, that's going to be an e to the -infinity, plus 1/5, -5 times -infinity is going to be a positive infinity. And usually when I'm dealing with e to the infinity or e to the -infinity, I like to rewrite the terms so the exponents are positive. And so that e to the -infinity, you could write as a 1 over e to the positive infinity. And that helps me see what's happening here. The first term, the -1 over 5 e to the infinity is on the bottom. We're taking a finite number divided by something that is growing without bound, and that's going to go to 0. But the second term, the e to the infinity, is technically in the numerator. It's not in the denominator. And so this one is going to equal infinity. Because I didn't get a finite number, that tells me that this integral diverges. So to summarize, when you're dealing with these improper integrals, My advice is keep track of where your infinities are. If they're in the denominator, that term is probably going to go to 0 because a finite number divided by infinity will always go to 0. All right, that's it. Let me know if you have any questions.